Exercise of the day. It was a distillation problem similar to what you're going to do in the homework. So this is the system we're working with. The first problem, how many stages does this distillation column have, and what is the feed stage? So let's count the columns. We're going to count off the operating line. So 1, 2, 3, 4, 5, 6. So we have 12 stages. No. Why is that wrong? You count off the equilibrium line, right? So we have 11 stages. Now, who can tell me how do you identify the feed stage for the column? Yes, Eric.
It's the stage after which the operating line regulates.
Okay, so when the operating line changes, that's going to be the feed stage. So stage 5 is the feed stage. Now, what is the L over V in the stripping section, and what is L over V in the rectifying section? And then what is the temperature in the cooler? Let's find out. So for the ratio of the rectifying section, we're just going to take two slopes. We're going to do rise over run, right? That's L over V. So for the rectifying section, L over V is 1.29. Does that sound right to everyone? For the rectifying section? No. Which one's the rectifying section? Top. So what did we just find? Stripping. So we found the L over V for the stripping section. Right? So now there's some confusion in the problem, and well, it asks you to find the ratio of the liquid to the vapor, I think. Is that what it asks? Yeah. And there's some confusion on, well, they were doing run over rise, because this is the liquid and that's the vapor. But remember, for the slopes of the operating lines is L over V. Dan had a great explanation last week on why the slope of the operating lines are L over V. Dan, do you want to give that for us one more time?
Because X and Y are mole ratios. Well, so XM is the amount of M over the amount of liquid, and YM is the amount of M over the amount of vapor. So Y over X is M over V divided by M over L, so the M's cancel and the L comes up to the top.
Exactly. Thank you, Dan. So the slopes of the lines are L over V. So don't forget that when you're working on distillation columns and for the exam. So next, for the rectifying section, again, we're going to find the points that are easiest to identify on the line, then we're going to do a standard slope. So L over V for the rectifying section is 0.78. So the temperature in the cooler. So the first thing we're going to do is identify the composition of the feed stage. They say that the feed enters in at the same composition of the feed stage. So we look at the operating line, the equilibrium line for stage 5 to get the feed composition. And then we go to our temperature XY diagram. Now we're going to plot the vapor and the liquid compositions to identify the temperature. So what temperature do you guys get? So around 79 degrees Celsius. So that's the temperature for the first cooler. Now the flow rate of the product stream. This goes back to mass balances. How do we approach this one? Just do an overall mass balance. So once we do an overall mass balance, we can kind of ignore the purge stream. It's just 0.001%. It's insignificant. Since the reaction is just E to M, what's going in is coming out. So the flow rate M out is 52 moles per minute, 98% N. All right, the flow rate of the vapor stage in the condenser. This gets a little bit more complicated, but again, it's just going to be a simple mass balance. So what do we isolate? We draw our boundaries around the condenser and the splitter. Let's take a better look at that. So our first equation is we know vapor going in is going to equal the liquid and the product coming out. So we have that relationship. But we have two variables that we're solving for. What's another equation we can use? Eric. Okay, so we know L over V is 0.78. Just make some substitutions, and we get the vapor to be around 240 moles per minute. All right, so now we're changing the conditions of the reactor, and we only get 40% M out. So we got 40% coming into the feed stage. Now the problem is, does this change any of the operating conditions for the distillation column? So we have the same liquid vapor compositions at 79 degrees Celsius. So we draw that on here. So now there's going to be no change in operation because the feed stage coming in at 40% liquid, M liquid, still fits into the tie line. So if the feed stage fits within the tie line for that cooler, it's not going to change any of the conditions because we're going to get the same liquid and vapor compositions coming out of the cooler. Now what about 30%? 30 more percent? Any ideas here? Does 30 more percent fit within the tile line? No. So what do you guys think we have to do? Yes.
Raise the temperature of the cooler.
Okay, but we are going to do that. But first, we need to change the feed point. So yeah, we're going to change the temperature of the cooler. But we have these constraints that we still have to meet. So we have 30% M feed must be in the fifth stage. And we know L over V compositions must be on a tile line that XM.3 intersects. We also know that the bottom's composition and top's composition still have to be the same. So the real technique here is guess and check. You'll get better at this throughout the years, don't worry. So we're going to make the first guess. We know these two endpoints on the operating line. And then let's just try some new rectifying and stripping operating lines. And let's see what happens. So we still want to get 11 stages, and we still want the fifth stage to be where the operating lines change. So we got the fifth stage here. We still have 11 stages. We adjusted the L over V's. So the L over V for the stripping is now 1.52. The L over V for the rectifying is now 0.82. And we have our composition, the stage 5, 0.27 liquid, 0.48 M in the vapor. Let's see if this fits, if 0.3 fits within there. Does it?
Yes.
Yes. So the temperature of the new cooler is going to be around 81 degrees Celsius. And the conditions that we just changed. So we just adjusted L over V for both the rectifying and the stripping sections. So really there's many solutions to this problem. It's really just guessing and checking, changing the slopes and seeing where's the fifth stage, where's the composition of the fifth stage, meet these requirements that 0.3 fits within the vapor liquid composition. So now the minimum amount of N. Does anyone have an idea of what we do next to find the minimum amount of N? So the lowest composition of N coming out of the reactor that we can still achieve a separation, a product stream of 98%. Any ideas? So what could we do? What would our where would we place our operating line to create the least amount of state, or get the stage farthest to the left? The first stage farthest to the left. Shane?
You increase the slope as much as possible.
The slope of the stripper should be very high.
Okay, so I actually decided, ignore the stripping section, we're just going to focus on the rectifying. So really, the rectifying section is what's going to achieve your 98% tops, right? Not the stripping. And the question asks, well, what's the lowest percent on the reactor of N that we can achieve the top separation of 98%? So I'm not even going to look at stripping. I'm just going to look at the rectifying section, and I'm going to run the column, the rectifying section at total reflux. So the slope of the operating line is just going to be the XY line, slope of 1. We have our fifth stage down here. So our feed stage is around, the feed composition is around X equals 0.065 and then Y is 0.19. And we're going to take this back to the TXY diagram. So we know the cooler is going to be at 85 degrees Celsius now. And the minimum overall composition, since it needs to fit within this tile line, but we want the lowest composition, we can say 7% coming out of the reactor. So 7% coming out of the reactor just fits within the tile line, and will still achieve the separations that we need for the feed stage on the previous distillation column. So 7% is going to be the lowest composition that we can come out of the reactor and still achieve the top separation. Does anyone have any questions about that last part? Yes, Shane?
So I always think that last part's hypothetical because you can't run it.
So if we were to run a total reflux, that's saying
Run it.
you get very little distillate, so barely any distillate. So you have almost no product stream out. But it's feasible you could get maybe slightly a little bit.
I see.
But you wouldn't really practice this in industry.
But it's good to know the limit.
Yeah.
Right.
All right. That's it.
Thanks, Andrew.